Hello again, everybody. In this video, we're going to go deeper into the idea of an equivalence class and also give some examples of equivalence relations and their corresponding equivalence classes. So in the previous video on equivalence relations, we looked at this example of 12 dots arranged nicely so that we could draw some boundaries around them, right? We look at some subsets, and I think I did these vertically. So I broke this up into 4 distinct subsets. Okay, so these are disjoint subsets. And we mentioned that each one of these is going to form an equivalence class, right? So again, we labeled these something like A, B, and C. And we said that A was equivalent to B, right? And similarly, B is equivalent to A. Or we wrote down what we called an equivalence relation E, which was a subset. Well, if the whole set is called S, then this was a subset of the Cartesian product. And in this case, A comma B then is an element of E. So when we are only interested in the entire equivalence class, not which element from the equivalence class, then we might use some notation to indicate which class we're talking about. So for example here, I might use maybe some square brackets and put it around A. And by doing so, I'm saying, okay, this is the equivalence class of A. So the equivalence class of A, denoted like so. And in different contexts, we'll use very different notations to denote these equivalence classes. But the equivalence class of A denoted by, say, in this case, square bracket A equals or is the set. Okay, so it's going to be all elements of S such that A comma X is an element of E, which in this case, we know what those elements are. What are the elements of S which are equivalent to A, right? There's going to be, well, A itself. We know that A comma A is in E, so that's A. And then B is equivalent to A, so we get B. And then C is equivalent to A. So that is what our equivalence class of A is. Now, you might rightly point out that A is sort of arbitrary here, right? We could have asked for the equivalence class of B. And, well, what would we get? If we asked for the equivalence class of B, well, then this would be all elements such that B comma X is in E. Okay, but again, we know that A is equivalent to B, so A would be in here. And we know that B is equivalent to B, so B would be in here. And we know that C is equivalent to B, so C would be in here. So in fact, we know that the equivalence class of A is equal to the equivalence class of B. And for the same reasons, this will also equal the equivalence class of C. So when we take the equivalence class and we write it down using this notation, we don't really care so much which element we put in here. It's not going to change what the equivalence class is. Now, this is going to cause us some issues down the line when we try to put binary operations on the set of equivalence classes. Because if we use the element that is defining the equivalence class, and then somebody else uses a different one, that might be problematic when we try to define this binary operation. And we'll see that when we do modular arithmetic, and maybe even a little bit when we talk about the rational numbers. All right, so let's do, well, actually, let me first finish by saying, okay, let me give some more names here. So I have D, E, and F, and maybe this is G, H, and I, and then this could be J, K, and L. So one very useful thing to do is to choose one particular element from each of these so that we get all of the equivalence classes. So if we choose a subset of S that contains exactly one element from each equivalence class. Okay, so how could we do that up here? Well, maybe I'll just choose them sort of arbitrarily. I could choose B, and how about D, and G, and L. Okay, I just chose one from each. I did it in just a reasonably random way. Okay, so if I do that, then we call that subset a set of representatives. Oops, representatives of the equivalence classes. Okay, or sometimes it's called a transversal. Okay, so the trans, right, that always means across. So this is something which is cutting across all of the different equivalence classes. All right, so this set of representatives should be, maybe it should invoke things like maybe your system of government, where you say, oh, well, we maybe have a representative democracy, and so we don't actually have one vote on, for say there's some bill, not everybody in the country gets a vote on it. Instead, we have equivalence classes. People are in districts, right? Those are the classes, and a representative from each district. Okay, that is the set of representatives of the equivalence classes, right? They form a transversal. So that's what Congress is, right? At least like the House of Representatives, right? They are a transversal. Okay, so so in this case up above, we had a transversal, right, or a set of representatives, and the transversal was B, D, G, L. Okay. Of course, we could have chosen any of these elements from each of the sets. The only thing you couldn't do, right, is choose two from the same. So you won't have a transversal that contains both D and E with this equivalence relation. All right, so let's get to some examples. So the first example I want to talk about goes back to Euclid. All right, and Euclid, of course, right, father of geometry, if you like, wrote the Elements, and in the Elements, he talks about parallel lines. Right, it turns out to be one of the more controversial parts of Euclid's Elements. So let's say we have, well, you have all these lines in the plane, right? And so, okay, here's some lines which at least are supposed to appear to be parallel. Then I have some other lines, right, which are not parallel to the first ones, and then I have some more lines, right, which are supposed to be parallel to each other. Okay, so I'd write down all possible lines. That's a lot of lines. Okay, so I might have as my S the set of all lines in the plane. And I would like to put an equivalence relation on this set based on parallelism. All right, so I'm going to call it, say, P instead of E. So P, this equivalence relation, okay, so this is going to be a subset of S cross S. And we're going to say that if you have two lines, so for two lines, say, I don't know, L and M in S, L comma M is in P, so this means they're parallel, right? If L is parallel to M. All right, now the question is, does this form an equivalence relation? And so, of course, we might use notation here to shorten things up, right? L parallel to M. We know, of course, that if a line L is parallel to M, then this implies that M is parallel to L. Of course, we also know if L is parallel to M, and say M is parallel to some other line, say N, then L will be parallel to N. So we have our symmetry and we have our transitivity. Okay, what are we missing? There was a third condition, and that was reflexivity. So reflexivity would say L is parallel to itself. All right. And this is sort of a convention question, really, right? If you define parallelism as meaning the lines never intersect, well, L intersects itself all the time, all right? So if parallel means never intersects, then no. It's not, L is not parallel to itself. On the other hand, you might say, well, two lines are parallel if they have the same slope. So if parallel means same slope, well, sure, L has the same slope as itself. So then the answer would be yes. All right, so you might start to appreciate the importance of definitions, right? You might say, well, yeah, what could it matter if we choose parallel to mean it never intersects or that they have the same slope? It means the same thing, right? Well, it could actually have some impact. So if you are very interested in having an equivalence relation based on parallelism, then you definitely would want to define it, say, as the same slope, or something else that would allow for this reflexive property to happen. If, on the other hand, you are really interested in things like do lines intersect, which in a lot of geometry, that's a big deal, well, then you're just going to have to give up this equivalence relation, right? Okay, so this is how we could potentially build an equivalence relation if our definition of parallelism is okay. All right, what's another example? Well, if we stick with Euclid for a moment, you may recall that there are these things called triangles. And sometimes you're able to take a triangle and move it over somewhere else, right? And you say, oh, okay, cool, now I've got two triangles, right? And you ask, are they the same triangle? And in a strict sense, no. I got, let's say this is triangle 1, this is triangle 2, and I know they're not the same because triangle 1 is over here and triangle 2 is over here, right? Those are clearly different triangles. On the other hand, for a lot of purposes in geometry, we want to be able to treat these triangles as if they were the same. All right, what is the same? Well, the word in geometry uses congruent. What does congruent mean? Well, we're putting an equivalence relation on the set of all triangles. Right? So we put an equivalence relation on the set of all triangles. All right? So when are two triangles equivalent? Well, if they have all the same, say, sides and angles, right? So two triangles are equivalent if, well, okay, we say they have the same sides and the same angles, but of course, we may not have oriented this the same way, right? So it might have been, turned into a different direction, right? And you say, oh, okay, so after I rotate it or something like, there's some way to correspond the points so that all of the line, the lengths of the sides and corresponding angles are the same. So if there is a correspondence of vertices such that corresponding sides and angles are the same. All right, one possible way of saying it. Okay. So congruency, something you spent a lot of time doing in geometry, is really an equivalence relation. Okay. Incidentally, right, similar triangles, right? So that notion also gives an equivalence relation. Okay. Now, let's talk for a moment about the equivalence classes. So when you have a congruent equivalence relation, right, congruent triangles, then you just pick one triangle from each congruence class, right? So you take a triangle and you say, okay, what are all the possible congruent triangles? And I just pick one of those. All right. Okay, if you do similar triangles, well, now I might have, say I have like an equilateral triangle. I can write down all triangles which are congruent to this. So maybe I have one which I've rotated a little bit, but it's still congruent, same side, same angles. All right, so all of the congruent triangles are going to be in the same equivalence class still, but now we also get scaled versions. All right, so I would also get these. And if I'm actually looking at equilateral triangles, well, they're all similar to each other, right? Because they all have the same angles. The only difference is the size. All right, so all equilateral triangles form a single equivalence class. All right? Whereas with congruent triangles, if you were looking at equilaterals, each size would form a different equivalence class. So all equilateral triangles for the congruent side of different sizes form or represent different equivalence classes. Okay, so changing your equivalence relation will change your equivalence classes. All right, I'm going to do one more example because we're running a little bit long here. But last example, this is one that you've known for quite a long time, which is the following. Let me take pairs of integers. Okay, so I'm going to look at the set of all integer pairs. So A is an integer and B is an integer. However, I don't want B to be 0. Okay, now why don't I want it to be 0? Well, because what I'm thinking about here is actually looking at fractions. Okay, only instead of writing it as this fraction, which is this new symbol, I just want to write it as a pair, A comma B, and then the order matters. And of course, I can't divide by 0. If I did, a puppy would get kicked. Okay, now we know that if I replace A over B with 2A over 2B, it should be the same fraction. Which means, I mean, from the point of view of the set, it's not, right? Like if I had a pair A comma B and a pair 2A comma 2B, I mean, those are just clearly different, right? These are not the same thing. So what I want to do is put an equivalence relation on this set. Okay, we'll just call this S for right now. So what is the equivalence relation? So we want an equivalence relation on S. So I'm going to say that, well, let's see. Let's say I have an A comma B and a C comma D. And when is it going to be in our equivalence relation? Which, okay, well, again, we'll just call it E. If, well, what is it we want? We want to know when does A over B equal C over D? Well, if we multiply both sides by B and by D, this is equivalent to saying that A times D is equal to B times C. So that's going to be our condition. Two different pairs, right? Remember, these are our fractions. Two fractions are equivalent if the first component of the first multiplied by the second component of the second is equal to the second component of the first, the B, times the first component of the second. Okay, and with a little bit of effort, you can show that you have an equivalence relation. And if we just take representatives, right, and then we build equivalence classes, right? So the set of equivalence classes right? Well, and what is an equivalence class, by the way, right? So we are using square brackets to denote an equivalence class, but you know what? Let's just call this A over B. Okay, so the set of equivalence classes equals the set of rational numbers. So we actually, if we want to define rational numbers, we actually define them as equivalence classes of pairs of integers where the second component is non-zero. Right? Now, we're probably used to seeing or thinking of the integers as being a subset of the rational numbers. And if we define the rationals in this way, then that's not strictly true. Right? The integers, okay, you just got these numbers. Q, right, the rationals, those are actually pairs, and not really even just pairs, but equivalent classes of pairs of integers. However, there is a way of making this all make sense, which is we could write down sort of a copy of the integers inside of Q. Right? So let's call this Z bar. And so this is going to be all, well, if we're doing equivalence classes like this, all things of the form A over 1, where A is an integer. Okay, so these are all the equivalence classes where the second component of a representative is 1. All right, so remember, of course, A over 1, this is equal to the set of all things of the form. Well, let's see, it should be all, how about C comma D, such that CD is equivalent to A1. Okay, well, what does it mean to be equivalent to A1? Right? Well, this part here meant, well, we got to use this relationship, right? C times 1, so this is equivalent saying C times 1 is equal to A times D. All right, so C times 1 is equal to A times D, and so if you like, C is equal to AD. All right, so this should be all things of the form AD comma D, where, what is this D? Well, D, of course, could be any integer. All right, so D is any integer. So this makes sense, right? What is an integer? It's really just, if you like, it's a pair of integers. Okay, that's a little bit circular there, right? But we really mean a rational integer. A rational integer is a pair of integers where the first component is some fixed number times the second component. Okay, I don't know, that's really, really weird. We're going to have to, go into that in greater detail in the future, particularly when we want to put binary operations on Q now, because it's going to mean we're going to have to put a binary operation on equivalence classes, and it's going to really matter which choice of equivalence of a representative that we choose, right? Or at least it could. All right, this is a bit long, but hopefully you get enough out of it, and we'll see you in class.